Okay, so let's take a look at example 2. So we're given this vector field here. So let's label the components P and Q. So as a reminder again, the fundamental theorem of line integral only applies when your vector field is conservative. So what we need to do is to verify this vector field is conservative first. So as usual, we need to calculate the partial of P with respect to Y and the partial of Q with respect to X. So the partial of P with respect to Y, so this just becomes 2Y, and then 2 times 3 is 6. So you get 6x squared Y, and the partial of Q with respect to X. So this part is 3x squared. So 3 times 2 is 6. And then we have the x squared, the y is still there, and the derivative of a constant is 0. Okay, so we see that the two partial derivatives that we calculated here are equal, so f is conservative. Okay, so now we need to go ahead and find the potential function. So we need to calculate two integrals. So the integral of P with respect to X, and also the integral of Q with respect to Y. So what was P again? That was 3x squared Y squared. And what was Q again? It was 2x cubed Y minus 4. Okay, so here I'm thinking of y as being constant, right? So the antiderivative of x squared is x cubed over 3. And then I have my constant term, right, which in this case would be g of y. And then let's calculate the second integral here. So I'm integrating with respect to y, so this is y squared over 2. And the antiderivative constant is the constant times the variable, which is y. And then I have my constant term, which contains x. Okay, so now let's compare the two results, right? So 3's here cancel, the 2's here cancel. Right, so the x cubed y squared is the same for both. This term here is my g of y, and then there's no other term here, so that means that h of x has to be equal to 0. Okay, so this should be our potential function. Right, so the common term again was this one, which was x cubed y squared, and then my g of y was the minus 4y, and then h of x is 0, so there's nothing else. And then, as usual, let's just quickly check. F sub x should be equal to p, and f sub y should be equal to q. Right, so f sub x is 3x squared y squared, which is exactly p. And f sub y should be, so this is 2y, so 2x cubed y minus 4. 2x cubed y minus 4. Okay, so so this checks out. So this is our potential function. Okay, so now we're ready to apply the fundamental theorem of line integrals. Again, it only works for conservative vector fields. And again, we've already verified that it's conservative, so we're allowed to apply the fundamental theorem of line integrals. Okay, so what does it say? It says that my line integral of f dot dr, again, this has to be conservative, this line integral can be calculated by just substituting the endpoints. So x2 comma x1, whoops, x2 y2, that's the endpoint, and then the starting point would be x1 y1. Okay, so what is the starting point and the endpoint? So let's go back in the problem. So this is the the curve C. So the starting point is when t equals 0, and the endpoint is when t equals 1, right? So let's calculate it here, right? So x2 y2 would be plugging in 1, right? So we're looking at the endpoint first. So plug in t equals 1. So what do you have? What is this? 1 minus 2. And then this is 2 minus 1, which is negative 1 comma 1. And then x1 y1, you plug in 0, which is equal to 1, this is just 1, and then this is just 2. Okay, so negative 1 1 and 1 comma 2. So right, so these are 2 points, negative 1 1 and then 1 comma 2. Okay, so I have to plug that into my potential function. Right, so let's calculate it here. Right, so negative 1 cubed times 1 squared minus 4 times 1. So that's this calculation, and then minus 1 cubed times 2 squared minus 4 times 2. Okay, so what is this? This is negative 1 minus 4. And then this is 2 squared is 4. 4 times 2 is 8. So this is 4 minus 8. Okay, so this is negative 5 minus a negative 4. And so that's a plus 4. So this is equal to negative 1. Okay, so so this is how we calculate this line integral using the fundamental theorem of line integrals. So actually, alternatively, you can try to calculate this line integral directly. So I've already sort of started it here on the next page, right? So if I were to calculate the line integral directly, so if you remember, the setup is the integral from a to b, and then you have to plug in x of t and y of t into p and q, and then it's dot x prime y prime, right? So r prime of t, and so if you write it out, it'll look like this. And so it would mean calculating this ordinary integral. So, I mean, you'd have to expand this out, but basically this is just a polynomial. So it's possible to calculate this. So you sort of have to determine for yourself whether trying to find the potential function like this and then applying the fundamental theorem of line integrals, is this calculation easier than this calculation here. But if you actually do proceed with this calculation, you can check that the value should be equal to negative 1. Okay, so that's how we apply the fundamental theorem of line integrals.